Alright, this is chapter 12. So the title of this chapter is basically vector valued functions, which sounds awfully fancy. You could possibly better think of this or title this as motion of objects. Because even though that's not the only use of vector valued functions, that's a really good use, and it's a way of helping us understand what's going on. So the general layout of the chapter is we're going to introduce vector valued functions, draw a bunch of pictures, talk about derivatives and integrals, things related to that. So 12.1 is, like I said, primarily definition and examples. And so I'll give an official definition, and then basically the rest of the section will be just blasting through a whole slew of examples and a lot of pictures, because pictures will be really, really helpful here. So now, funnily enough, we've seen a vector valued function before, but we didn't use that term. But a vector valued function which I'm going to abbreviate VVF, so we could be a bit lazy. This is nothing more than a function which inputs a real number and outputs a vector. Let's say which takes in, in other words, the domain takes in real numbers and outputs vectors. So a few examples. And because it outputs vectors, the function name will have a bar over it. So something like r of t equals 1 plus 2t I plus 4 plus t j. Right? Now this should be familiar, because this is the vector equation of a line. However, none of the next ones on our list will be familiar, but they will have the same feature, is that in goes a real number, out goes a vector. So t squared I. Here I'm just making up, I'm just dumping in functions. Really don't worry about what we're getting here, other than in goes a number, out comes a function. Could be two-dimensional, could be three-dimensional. They don't have to be functions. You could have a constant there, like this. 2i plus tj. Say minus t cubed k, etc. So then, again, for all of these, we plug in real numbers. And out come the vectors. So, what's the use of these? Before we nail down some really specific examples and develop a vocabulary of problems that will be useful to us, or examples which will be useful to us, let's just mention one use of these. So, we will have a few, but a primary use, and the best one to mention first, is to describe the location of an object at a certain time. So the reason we use the variable t is as a time variable. So here, think of this as to describe the location of an object at time t. So for example, if we were to give the vector valued function something like r of t is, say, ti plus t squared j. We don't have to think of it this way, but we can think at time t, an object is at x equals t. This is the I component. And at y equals t squared, the j component. So just like when we had vector equations of lines, it may seem a bit odd to write these as vectors when we're talking about locations. But the reason for having this is because then they become like nice, simple, single objects. I don't have to list them as coordinates. Right? So these are vectors, but don't think of them as vectors. If you want to think about them as vectors, then just think about them. Think that r of t points from the origin to the object, if it helps. If having a vector notation bothers you, think about it this way. So for example, in this example, and the example above, like if we were to plug in a couple of t values, say r of 1 is 1i plus 1j, r of 2 is 2i plus 4j, I'll just do these 2 points. Then what we can think of it, you can think of it one of two ways. Right, you could think to yourself, okay, when the time is 1, at t equals 1, we're pointing to the point 1, 1, right here. And the time equals 2, we're pointing to the point 2, 4. That's way up here. This is not drawn to the best scale. This is 1, 1. This is 2, 4. So the vectors themselves, let me draw this in different, well, the vectors are also blue, but this vector is r of 1, and this vector is r of 2. So I guess in a sloppy way, we're using points and vectors interchangeably, but that's okay, right? The key is when we're thinking about these things as the location. So let me just re-emphasize that back up in the definition. We're thinking of this as the location. And this isn't the only use, but this is a great one for now. If we think about this as the location of an object, then just think of it as a point. So what we need to do next is we need to go through a bunch of examples of these. So as we go through the rest of the chapter, and really the rest of the course, we need to have a certain vocabulary, right? So the reason is, like in pre-calc, when you learn what a function is, you memorize a bunch of functions, right? You memorize say parabolas and absolute values and sines and cosines and cubics, and you do that so that you can have a discussion, so that you and your fellow students and teachers and people in the mathematical community can all talk about these functions without having to look up everything. So you're developing a vocabulary so you can have conversations about functions. So we need to do the same thing here. So what I'll do for the rest of this section, basically, there's a little bit at the end that's not this, but basically is just do a bunch of examples and talk about why these vector valued functions look like they do. And so the first thing I need to do is I need to make sure it's clear what we mean by the graph of a vector valued function. So I'm going to clear the screen, I'll mention that first, and then we'll just work through a whole bunch of examples. So 3. Graphs of vector valued functions. So definition. So this is why it's good to think of a vector valued function as giving you the location of an object. So informally we can think of the graph of a vector valued function as a plot of the path, or the route if you like, the object takes as t covers its domain. So this little side comment about t covering its domain, that may be confusing just right now, and that's okay. Don't worry about that. So here we will do a whole bunch of examples. So let's look at this one. We'll say r of t is, say, 1 plus 2ti plus 3 minus tj, and I'm going to give a domain of t's, right? So I'm not going to say that t could be everything. I'll say, for example, in this one that maybe t can be between 0 and 2. So two things. First of all, we know that this is a line because we know that this is the vector equation of a line. But even if you didn't know that, right? Suppose you're back in pre-calc and you learn what a function is and you see your first function. The first thing you might do is you might plug in points. So just for a couple of times, let's just plug in some points and see, right? Just to see what happens. Now, we won't do this in general, but just to sort of get our hands dirty and figure out what's going on. Let's try some points. Or maybe more accurate might be to say try some t-values. So I will take a bunch of t's, just not too many, maybe 3 or 4. I will find r of t, and then I'll write down what point this is. So we'll do, say, 0. We'll do 0, 1, and 2. We'll just do 3. It'll be easy. So r of 0, when I plug that in, I get 1i plus 3j. So I think of this as the point 1, 3. When we plug in 1, we get 3i plus 2j. That's 3, 2. When we plug in 2, we get 5i plus 1j. So we plot these. Let's do this in different colors, say blue. We start at 1, 3, we're right here. So what I'm doing is I'm not drawing the vectors, I'm drawing the points that the vectors are pointing to from the origin. Then we have 3, 2. We have 5, 1. We see that this is a line. We draw this. And I'll put an arrow along the line, a couple of arrows, just to sort of indicate the direction of motion. This is t equals 0. This is t equals 2, just to get a feel for things. So in this case, the vector valued function is a line segment. Starts at 1, 3, ends at 5, 1. Nice simple example. Let me do a slightly different one. Let's do, say, cosine t I plus sine t j. And we'll say t goes between 0 and pi. Now, just for the record, most of these that I'm going to do at the beginning will be in two-dimensional space, just to get a feel for things. But fairly soon, within this section, we'll move to three-dimensional space. But 2 is a good place to start. So, this might look familiar to you, right? If you think about this as x is cosine t, y is sine t. If you remember from Calc 2, you did some parameterization of curves somewhat related to this. You might recognize this as a circle. I'll put a question mark there because you might not. So again, we can try some t-values. So let's do, say, 0. Let's do pi over 4, pi over 2, 3 pi over 4, and pi. There's no harm in doing a bunch. So we'll do r of t, and we'll do a point. Plug in 0, so cosine of 0 is 1, sine of 0 is 0. So we're at 1, 0. Plug in pi over 4, cosine and sine are both square root of 2 over 2. If your trig is a little rusty, you may want to review a bit. There'll be a bunch of trig that comes up in this course. Plug in pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. We get 0, 1. 3 pi over 4, cosine is negative pi over 2. Sine is pi over 2. Or it's, sorry, cosine is negative square root of 2 over 2. Sine is square root of 2 over 2. And pi, cosine is negative 1. Sine is 0. Now, just in case you're a bit rusty on this, the square root of 2 over 2 is about 0.7. That'll help us when we sketch this. So, let me label these axes. I should have done this over here as well. So if we do this in blue again, so we start at 1, 0, so we start right here. Now, if we do the 3 easy points first, 1, 0, 0, 1, negative 1, 0, we start to see what's happening. 0.7 is about here. Negative 0.7 is about here. So this is going like this. This is the direction. And I'll back here again, I'll put t equals 0 and t equals pi. So here we get a semicircle. It is a semicircle because of the pi up here that we're ending at. You could probably guess if we were going until 2 pi, we'd get the full circle. So we'll do that in just a second, because I want to start doing this and not do a table of t values. I just want to do that for these two so we can get a feel for things. So take a second, digest these. I'll do a couple more circles, and then we'll do a whole variety of other things. So let me clear the screen off and keep going. So digest these first. So clearly, I'm going to modify the previous one a bit. I'm going to make this a 2 cosine t I and a 2 sine tj. And we'll make t go all the way to 2 pi. So basically, this will be a full circle. And the radius will be 2. This is because the x and the y are multiplied by 2. So if you sketch this, and again, if this is confusing, like by all means, take some time, stop and on your own plot some points in. Like, there's no rush. It's better to do it slower. So when you start this at t equals 0, I'm going to begin out here at 2, 0, and then it's going to go this way. My circle may not be perfect, that's all right. And it ends right there as well. So t equals 0, t equals 2 pi. Up here will be t equals pi over 2, just for reference. T equals pi over here. T equals 3 pi over 2. Yeah, and again, it's going counterclockwise here. Now let me just do one more circle just to make an interesting point. So this point, like, I put these 5s in here, and you're probably going to guess correctly the radius is 5, and that's great. But what I'm actually going to do is I'm going to go back. Actually, what I didn't want to do is this. Let me tweak this a bit. I wanted to do 2t there and there. So here's the thing. Like, you might look at this. Actually, I have a bunch of little errors here. This is supposed to be a pi over here. Now that we have that all right. So you might look at this and you might say to yourself, well, this is going to pi, so it's a half circle. But then you might look at these guys and you might say, like, what do those 2's do? So here's the thing to think about, right, is when t gets to pi, two t has made it to 2 pi. So this is actually doing a full circle. It's basically sort of like going twice as fast, if you like. We don't have a good sense of speed just yet, or a definition of that. But think about what's happening. The 2t doubles the t value that's going in. So we do get it is radius 5. Probably correct in your assessment there. But in this case, it will make it all the way around. And this can be a bit confusing to people because t equals 0 is here. T equals pi over 2 is around there because at pi over 2, we're plugging in pi over 2, but then we double in and get pi. So we have the cosine of pi and the sine of pi. So the top is actually pi over 4, and the bottom is actually 3 pi over 4. And then it ends at t equals pi, makes it all the way around, like that. So let me do another circle. Actually, before we do one more circle, let me modify the circle one more time. There'll be a lot of circles. It's a familiar shape. So we'll do r of t equals 2 cosine ti plus 4 sine tj. So now if you look at the coefficients are different. And so you might guess that this is not going to be a circle. This is going to be an ellipse. All right, so this guy will stretch differently in each of the two directions. All right, in the x direction it will stretch to 2. In the y direction it will stretch to 4. And in this case it'll be a half circle because of the pi. We're not doing anything with the t inside the sine and the cosine. So it's starting over here. I drew it the wrong direction, but that is right. And it ends over here. And up here is the t equals pi over 2. Going all the way around. So that makes that ellipse. And then let me do one more circle. Let me do one more thing in 2 dimensions. And then we'll move into 3 dimensions. Just make one small change. I'll do 1 plus cosine t I and 2 plus sine t j. Oops, let me make sure that the j is outside of the parentheses there. And t will go 0 to, say, 2 pi. So the thing that changes here is I'm changing the x and the y. This first guy, this shifts it to the right. It increases x by 1. And this will increase y by 2. So the result is still a circle. It's just a shifted circle. So it moves the center. But the radius is still 1. So what happens is the center of this circle, let me mark the center in say green. The center of the circle is at 1, 2. It's right here. The circle itself is still radius 1. It's still beginning now over here on the right. This is t equals 0. And it goes up, still radius 1, comes down here, just like this. Over here is t equals pi. I'll just label those. Well, actually, let's label the top and the bottom as well. You don't need to label as much as I'm labeling. I'm just labeling a lot to help you grasp what's going on. Still going counterclockwise. So the 1 and the 2 shifted in that case. So again, take a second, look at these, look at what's familiar about them, look at what's different. Ask yourself some questions, right? If you wanted an ellipse to have certain features, how would you tweak the numbers accordingly? If you wanted to center an ellipse somewhere, how would you do that? Things like that. So use these examples that I give as fundamental examples from which to build off, right? Just like in pre-calc, once you know what a parabola looks like, you can shift it, you can stretch it, things like that. You don't need to memorize them all. You just learn the ideas. So same thing here. So let me move now into 3 dimensions. And I'm still going to stick with circles because they're familiar with us, but I'm going to tweak them just a bit. So again, let me clear the screen off, do a few of those. So let's do, so we're going to look like we're going back to basics. But we're going to add in a k component. Let's say. So when you see this, what you want your brain to do is you want your brain to look at the familiar bit. So you look at this and you say to yourself, hey, I know that. That's a circle. If you couple these two things together, this is a circle in the xy plane. This too, though, this says, no, wait. This is up at z equals 2. So what we'll do is we'll go to the axis. Now we have to be in 3D. Oops, let me do this in black. So what can help here is what I'll do is I'll draw like a very light circle in the xy plane as like a reference circle. You don't need to do this, it can help. So here is a circle in the xy plane. All right. This would be if I had, this can actually help, I'll do this. This would be if we had cosine ti plus sine tj just by itself, or if you like, plus 0k. Now what happens for our circle is I take it, I move it up by 2. So I'm just going to take the circle and do the best job I can. It doesn't need to be a work of art, move it up by 2. This would be centered at 2, up at z equals 2. Now in terms of where it begins, remember the original circle way back on the previous page started out at x equals 1. So we're going to start up from there. And so we're going to begin right there. This is t equals 1, or t equals 0. And the original circle went from the positive x-axis to the positive y-axis. So our circle goes around this way. So this is what happens if we have this circle. Let me do just one more now. One more 3D circle. Or 3D something. Let's do something like 2 cosine ti plus 3j plus 3 sine tk. This actually be fairly complicated to work out. There are a lot of little details here, right? So just like before, though, we'll start to rip it apart, look for the familiar things. Right? So the first thing we see is that the cosine and the sine, the things that are familiar, those are the I and the K. Right? So we see that these two, they form an ellipse. They're an ellipse because of the 2 and the 3. This is an ellipse in the xz plane. Now, then we look over here, the 0 to pi, we go, oh, it's a half ellipse. And then we look in the middle, right here, and we go, oh, it's at y equals 3. Because the j component is 3. Right? So what can really help us here is we can first say, look, let's forget the j for a second. Right? If we were in the xz plane, we would have this. So I will do this in like a mustard color like we did above. I would have something like this. Go from 2 in the x direction to 3 in the y direction, and then down to -2. Right? This is because of the coefficients 2 and 3. So then what I'll do is I'll draw 3 pictures for this actually. Then I will go into 3-dimensional space. Actually, I'll do 2 pictures, but one of them will have 2 things on it, as you'll see what I mean by that. So what I'm going to do next is I'm going to transfer this yellow picture. Right now, this yellow picture, just go back to it for a second, that has an arrow that goes this way. That's the direction it goes. I'm going to redraw this yellow picture on the new axis. So it begins at x equals 2, right there. It goes to the positive z-axis, and then back here. So it begins at 2, ends at -2, and goes up to 3. Then I'm going to take that picture, and I'm going to do the best job I can do of shifting it to the right by 3 units. So this is out at 3. Begins there, ends there. Now, let me go back to yellow. That guy still goes up like that, which means our curve goes up like that. It begins, just to give it some points, this is at x equals 2, y equals 3, z equals 0. It tops out at x equals 0, y equals 3, z equals 3. And it ends at the back here at x equals -2, y equals 3, and z equals 0. And that's our final sketch. Right? So by all means, like on a test, on a quiz, for example, whatever you're doing, if it helps to draw a few pictures, have at it. Like draw the pictures. Draw whatever you need to draw to have these things make sense to you. Don't don't try and jump just to the final picture if things are not making sense to you. Now I'm actually going to interject an example in here, which I'm not going to plot. I'm going to make a comment about it, and then and I'll make a couple comments about it actually, because so normally when I'm teaching this in person, a question I'll get from students, which is a really good question, is like, well, what happens if there are sines and cosines everywhere, right? Like all three of them. Like, what if you had something like this? I've seen these in textbooks before. Like, they've actually assigned these in homework. It sort of makes me ill. Because what's happening here is it's doing like a trig function, like a sine wave kind of thing in all three dimensions. This is very hard to visualize. Right? These are great examples to do if you can do them in software. So I like to put these on MATLAB assignments, for example, because you can code it up and you can just see and you can play with the pictures. But the combination of these, this makes it fairly hard. Right, so I wouldn't worry about these. I wouldn't worry about doing them by hand. They're extremely challenging. Even if you plot points, they sort of go around in circles, but they oscillate as they go around in circles, so they're not easy to do. So I want to do a few more. I want to do one more that has sines and cosines though, and then I want to sort of throw out like an esoteric collection of things that don't fit these formats easily, right? So let me clear the screen off, do another circle one. It won't fit in the picture in the space down to the right, so I'm going to clear things off, and then we'll keep going from there. So this one I'll do. I will have something besides just cosine and sine though. So we'll do cosine, sine, and we'll do like a tk. And we'll do t is greater than or equal to 0. So this is tricky enough to be interesting, but not so tricky as to be impossible. So again, you might look at this, and you might look at the first two, and you might be like, oh, that's a circle. Then you might look at this bit right here, and you might say, well, wait, as t increases, this goes up, because this is the z component. It's the k component, which is the z when we're plotting it. So the object, if you're thinking of it as an object, goes up. So when we draw this, what I'll do first is I'll draw that circle. Right, so that's a circle of radius 2. Begins right here, goes around. Again, this orange circle is if there was no z. Goes this way. And it would just go around in circles forever and ever and ever. And again, it has radius 2. So this is at 2, 2. Now, in our case, though, as it increases, it goes up. So it does begin here. Our thing begins at 2, 0, 0. But then as it goes up, when it gets over to the right-hand side, it's actually increased up to here. Because the yellow circle would have gone 0 to 0, but our thing, this is at pi over 2. Right? So just so we're clear, this is at the beginning, we're at 0. Over here, we're at pi over 2. So this is actually pi over 2. So about 1.56. So it's gone up about 1.5 units. Right? And then as it goes, it keeps rotating. So the spirals. Oops, spiral, that's a bad word. That word doesn't exist. Spirals up forever. And because as the t is increasing, so for example, like back here, where it's done a full circle, when t equals 2 pi, it is at 2, 0 again, but now it is up at 2 pi. It is 6.28 units approximately above where it started, because it's done a complete circle in the ij direction, but it has raised up in the k direction. So think about examples like this. Like, what if the t were in the middle value? Things like that. And then last but not least, for circles. Again, I want to move out of circles in a second because we're sort of belaboring those. I want to look at, again, a common question that comes up. We'll go back to 2 dimensions for this. It'd be something like, what happens if you mess around with the sine and cosine order. Right, so you might look at this and you might say, like, this is unfamiliar to me. Right, this is like, you might say, like, it's sort of the opposite from what you expect. Right? So I find it easier here, honestly, to simply go back and plug some points in. Right, there are lots of ways to think about this, but plotting some points can really be the best. And we don't need to plot a lot. We can plot like just 3, like a start, an end, and a middle. You probably have a guess that it's going to be a circle or a semicircle, and you'd be right. But just to really check it out, when we plug in 0, sine of 0 is 0, and 1, so we're at 0, 1. Plug in pi over 2, sine of pi over 2 is 1, cosine of pi over 2 is 0, and sine of pi is 0, cosine is negative 1. So what the sine and the cosine switching has done here is we are now starting right here, 0, 1. And we're moving to the right, so it sort of goes clockwise instead of counterclockwise. And then it goes to negative 1. So that change messed things up. So if those are in an unfamiliar way, my advice is plot a couple of points. It's not worth trying to remember what happens in every single possible order. So when in doubt, use your experience. Like here, you're like, I think it's probably a circle, semicircle, because of the sine and cosine. Plot some points and see, and you'll be able to work it out pretty easily. All right, so a couple of, let me do 2 that fit into a different model, and then we'll do a couple which are sort of just, different when all else fails. So next one I want to do is something like this. Ti plus t squared j, t between 0 and 2. This is not familiar. It's not like any of the other ones we've done, but it's actually surprisingly easy. The thing to see here is, remember what we're doing. We're plotting this like it's a point. So what we're thinking is oh, x is t. And we're thinking that y is t squared. But then you might notice that you're like, well, if x is t and y is t squared, put them together, that tells you that y is x squared. That's familiar, right? Now, over here we know that t goes from 0 to 2, and t and x are the same. So x goes from 0 to 2. This is because x is t. So when I sketch this, right, so take a second to, if you need to rewind and run through that in your head, go for it, right? But the idea is that x is t, y is t squared, so y is x squared. That's familiar. And x goes between 0 to 2. So when I plot this, I literally get the familiar y equals x squared. As x goes from 0 to 2, I get a parabola. So we get this. T equals 0, we're here. T equals 2, we're at 2, 4. Here we're at 0, 0. Let me be responsible. I'm trying to label my axes all the time. So let me do that here. I know I failed in a few places. So we get a familiar parabola, right? Now, this idea can be used a lot, right? So for example, anytime you see like a t in the first place, say, suppose you see something like this. Sorry, it's a sloppy I. Suppose you had ti plus, say, sine of t j. So now, same deal. You can look at this and you can say to yourself, hey, look, x is t, y is sine t, but that means y, if I put those together, that means y is the sine of x. And over here, this tells us that x goes from 0 to 2 pi. So we know what the sine of x looks like. This is a sine curve. Familiar. Doesn't need to be perfect. T equals 0 over here. T equals 2 pi. So t equals pi. goes up and down to 1 and -1. Familiar pre-calculus curve. Nothing sort of special going on there. Now, we could do the same if we put the t in the second location as well. So let me do one of those. Let me clear the screen off, do one of those, and then just sort of make a comment about anything that doesn't fit these criteria. So for example, if you had something like this, say we had e to the ti plus tj, where t is, say, 0 to 1. So now we look at this and we say, well, look, hey, here y is t. And so here, x is e to the t. So x is e to the y. Now, what you could do is you could say, like, well, this is kind of like y equals e to the x. But reversed. Right? Or you could say to yourself, oh, I could solve for y. Y is the ln of x. Doesn't matter how you think about this. Over here, you look at this and you say, well, okay, now this is t's between 0 and 1, but t is y. So y is between 0 and 1. So when we put that all together, right, the natural log graph, if you like, goes like this. So this is at t equals 1, is at y equals 1. This is at t equals 0. And if you want coordinates, you could say, for example, when t equals 1, this is at e comma 1. When t equals 0, this is e to the 0, which is 1 comma 0. This is going this way. This is a bit more confusing, but that's okay. It's still, we're just playing with ideas that we know. So lastly, anything that doesn't fit these, really you just have to plot some points, right? So when all else fails, plot points. Right, so for example, if you get this problem and you're like, well, what does something like this look like? Say something like this, right? So it's weird, right? Because you're like, well, it's just an I component. It's not clear if it's 3 dimensions or 2 dimensions. Let's do it in 2 dimensions. On a test, for example, I would say that, but like in this case, you know, we say like, well, you know, there's no y's, there's no j, there's no k, it's all x direction, right? And so if you plug in some points, you plug in, say, 0, and you get r of 0 is 0, so you're at the origin. And then as t goes up to 1, when t hits 1, r of 1, let me actually write some points down next to it, just so we're going completely crazy. So if I'm at 0, r of 0 is 0i, which is the point 0, 0 if we're in 2D. When t is, say, 1/2, just to do a middle point, we get 1/2 cubed is an 1/8, 2 times that is a 4th. And we're at 1, we're at 2i. So what this thing is doing is really just moving to the right. Right. Like that's it. It's really pretty boring. Right? T equals 0 here, t equals 1 here. T equals 1/2 is actually right here. It sort of speeds up as it goes along. But we can't really do any better than that. Like it doesn't fit a format. It's just plug in some points and see. And then for a last example, I'll do one that will remind you of a circle, but isn't. To say cosine, cosine, and say t will go between 0 and pi over 2. And so if you look at this, you might think that it's some kind of weird circle because of the cosine and the cosine. But the thing to see is that like these are the same. Right? X is cosine t, y is cosine t. So x is y. And so they lie along the same line. Right? They lie along the line x equals y. So when you draw this, right, if we plug in some points, again, because we might not really know what's going on, right? So we say, for example, say, let's do a little set of points on the right here. So t and r of t, when t is 0, we get cosine of 0, sine, which is 1. We get 1i plus 1j, so 1, 1. And then we get to the point pi over 2, we get 0i and 0j, so 0, 0. So what happens in this picture is, it's just a line segment, interestingly enough. I didn't actually need all this picture. It begins right here at 1, 1. Heads into the origin. And so what we're doing in this case is we're putting together two things, right? We're putting together the fact that we know that it lies on the line x equals y, right there. That's the diagonal line. And we figured out where it begins and where it ends, and then we're good to go. And that's it. So, like I said, look at these pictures. Really look at those pictures and variations on those pictures, and then don't sort of worry about it too much beyond that. Just memorize those, do examples of those, tweak those, see things like that, see what's going on. So the last thing I'll say, and I'm not going to belabor this too much, I'm literally going to jam it into the bottom here, is because vector valued functions, I'll call this a fact. This is just something to stick in the back of your head, but it's easy. It's just, I'm just saying this and it'll make sense to you. You could say, because vector valued functions are vectors, we can add them, subtract them, dot product them, cross product them. So for example, if I had one vector valued function like this, and don't worry at all about why you would do this. And if I had another vector valued function like s of t, say e to the t I plus 4j plus t squared k, then you can dot these. Again, don't worry about why you would ever do this. I just want you to recognize, like, hey, they're vectors. When you dot them, you do a dot product. You get a scalar. That's the result. All right, so just put that in your head. They're vectors. They behave like vectors. Everything's good. So that's the end of this section, end of 12.1, definitions and examples. So I'm going to call it quits there.